In this video, we will graph transformations of power functions. Power functions are the simplest type of polynomial functions. If we let n be any positive integer and have a coefficient a be any real number that is not equal to 0, we can write the function f of x equals a times x raised to the n power. We call this a power function of degree n. One power function you may have seen before is f of x equals x squared. In this case, n is equal to 2, which is an even number. We call this the square function. In general, power functions with even powers look similar to the square function. Another power function you may have seen is f of x equals x cubed. This is known as the cube function. Here we have n equals 3, which is an odd number. Power functions with odd exponents other than n equals 1 look similar to the cube function. We can use these basic power functions to graph more complicated power functions. Power functions have several characteristics that make them easy for us to identify. Let's first consider the case where n is even. When n is even, the graph of x to the n is symmetric about the y-axis. The domain of this function is all real numbers, so we'll write negative infinity to infinity. The range of the function is from 0 to infinity, because raising any value to an even exponent will always produce a positive value. Some key points that lie on this graph are negative 1, 1, 0, 0, and 1, 1. These points will always be on the graph of x to the n when n is even because, as we said, when we raise negative 1 or 1 to any even power, the result is 1. Similarly, 0 raised to any power will always be 0. The graph of this function looks kind of like the letter u, so the function falls from negative infinity to 0 and then rises from 0 to infinity. This means the function is increasing from 0 to infinity and is decreasing from negative infinity to 0. Now, let's consider when n is odd. In this case, the graph is symmetric about the origin, or the x-axis. The domain and range are both all real numbers, so we'll write negative infinity to infinity for both the domain and range. Some key points that lie on the graph are negative 1, 0, 0, and 1, 1. These points will always be on the graph because when we raise negative 1 to any odd power, we get negative 1. Similarly, when we raise 1 to any odd power, we will always get 1. As we said before, 0 raised to any odd power is 0. If we graph this function, we can see that it's always rising. Therefore, the function is increasing over the entire set of real numbers. So it is increasing from negative infinity to infinity. This also means the function is never decreasing, so we'll just write NA here. Now that we know more about power functions, let's try graphing an example. We'll graph the function f of x equals negative 3x to the fifth plus 2. Let's start by looking at the graph of f of x equals x to the fifth. From the table, we know this graph passes through the points negative 1, 0, 0, and 1, 1. Next, we'll want to look at the graph of negative 3 times x to the fifth. Since a equals negative 3, we know the graph will be compressed by a factor of 1/3. We also know that the graph will be reflected over the y-axis because a is negative. Here's the graph reflected over the y-axis and compressed. Using the same x-coordinates, we can determine that this graph passes through the points negative 1, 3, 0, 0, and 1, negative 3. Here, we can see that the graph of negative 3 times x to the fifth is decreasing over the real numbers. Now, we need to consider the vertical shift. For this equation, the graph will be shifted 2 units. Since 2 is positive, we will be shifting the graph up 2 units on the y-axis to give us the final graph of f of x equals negative 3 x to the 5th plus 2. We'll use the same x-coordinates again to find points the graph passes through. The graph passes through negative 1, 5, 0, 2, and 1, negative 1.